the sleigh started down to the homes where the Who's lay a snooze in their town. Oh yeah, this is stop number one. The old Grinchy Claus hissed as he climbed to the roof, empty bags in his fist. Then he slid down the chimney, a rather tight pinch. But if Santa Claus could do it, then so could the Grinch. Then he slithered and slumped, with a smile most unpleasant. Around the whole room, he took every present. Pop guns, pumpernoos, and cookies and drums, checkerboards, missile beans, popcorn, and plums. And he stuffed them in the bags. Then the Grinch very nimbly stuffed all the bags one by one up the chimney. You're a foul one, Mr. Grinch. You're a nasty, wasty skunk. Your heart is full of unwashed socks. Your soul is full of gunk, Mr. Grinch. The three words that best describe you are as follows, and I quote, stink, stank, stunk. You nauseate me, Mr. Grinch, with a nauseous super nose. You're a crooked turkey jockey, and you drive a crooked horse, Mr. Grinch. You're a three-decker sauerkraut and toadstool sandwich with arsenic sauce.
All right. Am I coming through? All good? All right. Happy Thursday, everybody. Welcome, welcome. Thank you for turning out for Backyard Astronomy this evening. I sure appreciate this. It looks like there's a good crowd. I know there's a lot of extra credit to be had, which is always a good incentive, but thank you for coming out on a relatively lousy night where there really is no prospect for using telescopes. I apologize for that, but you know, I am a weatherman, and there should be something I could do about it, but it is what it is. So we're going to learn about the wonders of the winter night sky tonight. By the way, I should mention, for my students at least, there is the sign-in sheet. Hopefully everyone saw that. Hopefully everyone, as you were coming in, got a hold of a lunar phase dial. We'll be using that in a few minutes, so that's good. For those students of mine who have signed in, you may have noticed there was an extra column in there. That extra column was to make sure that you stay through the entire talk. So you got to fill that out on your way out this evening. So I've hidden a few nuggets in the talk, so be attentive. The title is Twinkle, Twinkle, Little Star, because there's plenty of beautiful stars to talk about in the winter night sky. But before we even get into stars, I wanted to actually start out by talking about a closer friend of ours, which is the moon, also known as Luna. So before we reach for the stars, we're going to learn about Luna a little bit. And as I like to do when I'm teaching, I like to start out with a question. So the question is, how big is the Earth? Anyone know the diameter of the Earth? If I were to start digging from here, down through the center of the Earth and come out the other side, how far would I have to dig? A long way. 8,000 miles, approximately. 8,000, give or take a few miles. 78, 74. Where would I wind up, by the way? Not China, despite, you know, everyone says dig a hole to China. No, actually in the southern Indian Ocean is where we would wind up if we went straight down through the center of the Earth and came out the other side. So we know how big the Earth is. Diameter is about 8,000 miles. How about the moon? How big is the moon in diameter? 3,000? Not bad. It's obviously much smaller than the Earth. It turns out it's about 1/4 the size of the Earth. It's about 2,000 miles in diameter. So you can do the math, 8,000 for the Earth, 2,000 for the moon. And that tells us that, yeah, there's a ratio there, right? Ratio of the diameters, 3 and change. Let's just call it 4 between friends. So the Earth is 4 times the diameter of the moon. And we're going to do a little activity to start things out tonight, sort of a scale model activity, where we're going to let our, oops, I skipped through one? I may have. If I can go back. Yeah, so we're going to let our basketball represent the Earth. Okay, so I've got these 9-inch diameter basketballs. That's going to be the Earth. And so my question for you then is, how far away would you put the moon? Of course, the moon is going to be 1/4 the size of the basketball. So the moon is going to be a tennis ball. The question is, where would you put a tennis ball in relation to your basketball to show the proper scale in the distance? You know, if this is the size of the Earth and this is the size of the moon, how far apart should they be to reflect reality? Okay, so I'm going to spread some basketballs around. Look alive. Alive. Tennis balls. Yeah, if you would. Everyone sits so far back. There you go, Mr. Barnes. So you guys need everyone who gets a basketball needs a tennis ball as well. So the question is, where are you going to put your tennis ball in relation to your basketball? Another basketball? All right. Mr. Barnes has the remaining tennis balls there. So anybody who's missing a tennis ball, put arm up. Get Mr. Barnes. So where are you going to put it? How far away? What do you guys think? You guys are right front and center. Okay, so we got about 2 feet, something like that. 2 feet as well. You don't have to stand near your friend. You can, you can pass along to a friend if you think it's farther away. Okay, 3 feet, 3 feet. 4 feet maybe? How are we going to figure this out? Well, in order to figure out the proper separation, we need to know what the separation is in reality, how far the moon is actually from the Earth. And so to know that, there we go. What's the actual distance to the moon? It's about 250,000 miles. That's how far away the moon is from the Earth. And we're actually keeping track of the moon, believe it or not. The Apollo missions, they put mirrors up on the moon. And what we do currently is we shoot lasers up at those mirrors and wait for that light to bounce back. And by knowing the speed of light and by knowing the time of travel, we can figure out how far away the moon is. But it's approximately 250,000 miles, about 239,000 miles. I gave you this answer here. We already talked about how big your basketball is, right? The diameter of the Earth, 8,000 miles. If we know the diameter of a circle, what's the circumference of the circle? 2 pi r or pi d, right? Pi times the diameter. So we already know, didn't we just talk about the fact that the diameter of the Earth is 8,000 miles? So if we take that 8,000 and multiply times pi, what's pi? 3.14, right? Let's call it 3 between friends. 8,000 times 3, 24,000, right? That'll be the distance around the Earth. That's the Earth's circumference. Are you starting to notice a similarity between the numbers here? Essentially 240,000 for the Earth-Moon distance and about 24,000 for the Earth's circumference. There's another ratio, isn't there? If I divide the distance from the Earth to the Moon by the Earth's circumference, I get a ratio of about 10 to 1. So that means that if we could, let's say, wrap our basketballs 10 times, wouldn't that be 10 times the circumference of the Earth? And isn't that supposed to be equal to the distance from the Earth to the Moon? So, for everyone who's got a basketball in your hand, you need to have a little packet here which has a piece of either paper or piece of string that has been cut to the length of 10 wraps of a basketball. So Jensen's going to be around. She'll pass those out. If you put your hand up, let her know you need one. So go ahead and unwrap that. Unravel it. Let one person hold the basketball and one end of the tape. Then send your friend. Tell him to hoof it with the tennis ball in hand in order for them to have the proper distance between the Earth and the Moon, according to this scale. So we're going to use the string and ball to try it out. So from most guesses, I saw a lot of 2 feet. I saw some 3 feet, 4 feet. Obviously, 10 wraps around that basketball is a lot more than 2, 3, or 4 feet. Now, after you get it stretched out, don't go back. Don't go back. Stay where you're at. So once you get it stretched out, the person who's got the tennis ball, stay where you're at. Person with the earth, stay where you're at. Now, the person holding the basketball, once you get it all stretched out, I want you to take your pinky finger, stretch it out at arm's length, and hold it just kind of at the wall or something like that. Just kind of point it out there somewhere. And I want you to answer this question. Would your pinky finger, when it's outstretched like this, would it, let's say we had the full moon in the sky, would your pinky finger be able to cover that full moon? How many yeses? Yes, it'll cover it. How many no way, not a chance? That'll never cover the full moon. So I haven't heard there's no consensus here. Which is bigger, your pinky finger or the full moon? Well, you can, if you're holding the Earth right now, if you're holding your basketball, where's your moon? Isn't your partner who's got the tennis ball, aren't they holding the moon? Shouldn't you be able to try this out? So check by, instead of holding your pinky at the wall, go ahead and try to cover the tennis ball with your pinky finger. Does it work? Easily, right? So it turns out your finger, the width of your pinky finger, is actually much larger than what's called the angular diameter of the full moon in the sky. You can easily cover the moon with your finger. In fact, your pinky finger, outstretched at arm's length, is about 1 degree. So that means if you started from the horizon and put pinky finger, if you stacked your pinky finger 180 times, it would get you all the way to the other horizon. That's what being 1 degree in diameter means. So that means that it's bigger than the moon. So the moon turns out to be only a half a degree in diameter. So that means you would have to have 360 moons stacked on top of each other to go from one horizon through your, what's called zenith, your high point in your sky, all the way to the other horizon. So obviously our scale is indeed correct. This makes sense, that that's how far our tennis ball has to be in order to properly represent the true distance between the Earth and the sun, or the Earth and the moon. What's also relatively interesting is the fact that the sun is also about a half a degree in diameter in our sky. And that is just sheer coincidence. The sun is about 400 times the size of the moon, but it's also, how far away is the sun? About 100 million miles. Which is 400 times as far away as 250,000 miles, right? So therefore, the sun is 400 times bigger than the moon, but it's also 400 times farther away, and therefore it has the same angular diameter, which really comes in handy during, let's say, solar eclipses, where the moon is just the right size to cover up the sun's disk perfectly. Save the date, August 21st, 2017. Total solar eclipse. Not necessarily in our backyard, not in northern Mississippi, but relatively close. Like if you drive as far as Nashville, you'll be in the path of totality to see a total solar eclipse. How cool is that? Make your plans. Book your hotels today. If I'm still teaching, I guarantee I'm going to go, and I hope to take a group of students because that's a once-in-a-lifetime opportunity, not to be missed. All right. So we figured out our Earth-Moon model. All right, how about moon phases? If you now you can go ahead and have a seat. We're done with that activity. Thank you. If we had clear skies tonight, this is what the moon would look like. Anyone know what phase this is? It is a crescent moon. I'll give you that. It's a crescent moon because it is less than halfway illuminated. We break the moon phases down into how much of it is lit up. If it's less than half, it's a crescent. If it's half, we call it a quarter. If it's more than half, we call it a gibbous. Obviously, when it's fully lit up, we call it a full moon. When none of it is illuminated, we call it a new moon. And that's why you have that lunar phase dial that we brought in, that you brought in today. So here is how it works. What you need to do is you're going to hold it so that the horizon is horizontal. That kind of makes sense. And then you're going to rotate the back part of it clockwise so that your sun rises in the east, sets in the west. Your moon rises in the east, sets in the west. And that's the proper rotation for this thing. And what you'll want to pay attention to is the arrow in the middle, that guy right there. So the way I've got mine laid out, notice my full moon is rising in the east. What time is it? 6 p.m. What's happening to my sun? My sun is setting. So it turns out the full moon rises at sunset. And if you spin it around, what you'll find is that during the nighttime, the full moon's going to be in the sky, and then it's going to set at sunrise. So if that makes sense to you, that if you're reading this thing properly, you should find that the full moon rises at sunset. Sun's going down here in the west. Moon is rising in the east. And then if you rotate it around, swing this piece around until the sun rises in the east, the full moon will be setting in the west. Notice another thing about your dial. Your dial not only will tell you the different times that moon phases are in the sky, but it'll also tell you the alignment of the sun, the moon, and the earth for different phases. The way you figure that out is if you pretend that your little brad, that little connector, paper fastener, we're going to pretend that's the earth. In order to have a full moon, your earth has to be in between the sun and the moon. So if that makes sense, that'll hopefully help you answer this next question. And the next question has to do with the new moon phase. What does the alignment have to be? Computers. While we wait for that to reboot, I'll show you a planetarium program which is free, available to you, which is a program called Stellarium. I can move this thing out of my way. Nope, I can't. It shows what's currently happening in the sky. So right now, if we were outside, we would see in our western sky a very nice conjunction of Venus relatively close to our moon. In fact, let's check out the moon, if you think I was lying about what phase it's in. We can zoom in on it. And sure enough, that's the image that I just showed you a few minutes ago. Okay, so it is indeed in its crescent phase. And we're going to talk about which crescent phase. Turns out it's a waxing crescent phase. When the sun is brightening up, when it's lit up on the right side, it's called waxing crescent. That's waxing. And every day, tomorrow night, if the skies were clear, it would be a little bit more lit up on the right side. Now let me zoom back out. I'll give you a quick look at Venus since it's so nicely located close by. Venus is that bright evening star. A lot of folks think it's a star. It's not. It's a planet. And we're going to zoom in on it. And it turns out Venus goes through phases just like the moon does. Which that was a pretty big discovery by Galileo. And by the fact that Venus does indeed go through phases, including gibbous phase and crescent phase, that proved that the Earth was not the center of the universe. So it helped the Copernican model of the universe really take hold. But this would be Venus in a crescent phase. Venus is actually at its highest and brightest for the year currently, so that's kind of exciting. So that's why it's been so easy to spot in the evening sky. Let's see if we can get PowerPoint to be friendly again. So what does the alignment have to be to have a new moon? Where does the moon have to be in relation to the Earth and the sun? Remember, your brad, your connector, is your Earth. So notice where your new moon is. Where is it located with reference to the sun and the Earth? It's between them, right? Let's find our current phase. Our current phase is waxing crescent. So can you figure out when the waxing crescent phase rises? So use your phase dial and spin it so that the waxing crescent is just coming up in the east. And look at that arrow and see what time it's showing you. You get 9 a.m.? If you're reading it properly, you should be getting 9 a.m. The next question is, would the moon be visible at that time of the day? It always baffles my son. I've got three sons. My oldest son kind of gets freaked out when he sees the moon up during the day, because he thinks the moon only belongs in the night sky. But indeed, it can be in the daytime sky. However, I don't think the waxing crescent would show up at 9 in the morning. The reason being, what else is up in the sky? The sun. The sun always wins. The sun has a huge amount of light. So you can see the moon when the sun's not up because there's no competition. But when the sun comes up, now all of a sudden it's kind of like holding a candle. You can see a candle when there's no other competition. You put a candle in front of a floodlight, you don't see the candle anymore. So at 9 a.m., most likely the waxing crescent moon is not going to be visible. Let's try another one while I'm waiting for this thing to figure out. Mr. Seth, is the internet up? I'm having wireless issues. Wireless went down? Did that just happen? All right, well, we'll try another one. Let's see. We've done the waxing crescent. Let's try the last quarter moon. When does the last quarter moon rise? So when you spin that thing around, when does the last quarter moon? Midnight. Very good. Is it visible? You betcha. Why not? Why? Because there's no competition from the sun, right? When does the last quarter moon set? Noon. What's the proper alignment during that quarter phase? How must the sun, the earth, and the moon be aligned in order to have a quarter phase moon, either first quarter or last quarter? Can you see they've got to be at a right angle to each other? Right, they're going to form an L. Sun's got to be over here. Earth's got to be in the middle, and then the moon's got to be at 90 degrees from. I've got 3 children. And my youngest is fascinated with this book. Anyone ever see this book? Go Dog Go by P.D. Eastman. I think it's sort of a Dr. Seussish book. It's by the same publisher. And my youngest, who's, like I said, he's 2 years old, almost 2 years old, I'm constantly reading this thing, and a couple months ago when I was reading it, I came across a couple of pages. Again, I was hoping to have this projected, but there's 2 pages here. This one says, "Now it is night. Night is not a time for play. It is time for sleep. The dogs go to sleep. They will sleep all night." It's nice. "Now it is day. The sun is up. Now is the time for all dogs to get up. Get up. It is day. Time to get going. Go, dogs, go." And I read this for the 40th time. I got to thinking, those pictures are wrong. Why are these pictures wrong? I know this is kind of small. Can you see what moon phase this is? Waxing crescent, right? In fact, it's very much like tonight. What time is it? About 9, maybe, right? It's sometime in the late evening, right? Which direction is this window facing? West, right? Now it is day. Now is the time for all dogs to get up. Go, dogs, go. What's the problem here? Same window. So unless something happened overnight where the house went from being facing the west to facing the east, or perhaps those dogs had quite a night and they're not waking up till the following evening, yeah. These are the things I notice. My oldest son, his movie now is E.T. That's his favorite movie. And what's the movie poster from E.T. or the DVD case? What does that show? shows Elliot riding his bike with E.T. in the basket across a full moon, right? While watching this movie with my son, I noticed that just before that scene, like maybe a night or two before, when Elliot first finds E.T. and E.T. is in the backyard shed, Elliot kind of camps out in the backyard, waiting for E.T. to show up, and they show a waning crescent moon. And if you look on your lunar dial, notice that the waning crescent is pretty far away from full moon. How long does it take to get from, let's say, new moon to full moon? About 2 weeks, right? How long does it take to get from full moon to full moon? A full month, right? So to go the whole way around through the phases, through the cycle of phases, takes a month. So to get from new moon to full moon, about 2 weeks. So to get from waning crescent to full moon, we're talking probably about 3 weeks. And yet, we see Elliot in the backyard with a waning crescent one night, and the next night he's flying across the full moon with E.T. in the basket. Who worked our magic back there? Huh. Thank you, whoever did that. I was running out of children's stories. I only have 3. Only so long I can tap dance. All right. So like I said, here's a bigger picture of Go Dog Go. And again, we got the waxing crescent moon being lit up from the right side. So waxing crescent. Next day, now it is day. Right? All right. I meant to ask you, how long is a month? We kind of talked about that, didn't we? How long is a month? Yeah, on the calendar it's 30 to 31 days. Astronomically, the month is usually referred to as being the time that it takes to go through one full cycle of phases. Go from new moon to new moon, or full moon to full moon. In order to retain that, let's say full moon to full moon. To go from full moon to full moon, you want to have the sun, the earth, and the moon in a line. And of course, the moon is orbiting the earth, so it's going to go through its phases. And the time that it takes for it to get back to that straight line between sun, earth, and moon, that's what we would call a month. So that's about 29 and a half days. It's what's called the synodic period of the moon. But it turns out there's another period for the moon, which is, if we looked at the moon, in fact, we'll take a look at what constellation our moon is in currently. So there's the moon. And if I throw on my constellations, we can figure out that the moon is approximately in, let's see, what are we close to? I think we're close to Cassiopeia. So the moon is in a certain neighborhood in the background stars that we can see. And you can define the month as being, or the period of the moon as being, the time that it takes for it to get back to that same location among the background stars. And that's called the sidereal period. But it turns out the sidereal period, the time that it takes for the moon to get back to its place amongst the heavenly bodies, is a little bit less than the time that it takes to go through one full cycle of phases. And so therefore there's a difference in those names. The one is called the sidereal period. The other one's called the synodic period. The reason I mention it is because those are in a little song I wrote. So we're going to try that next. This is called Just a Phase, by the way. It's just a phase, 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 just a phase. Sometimes you're all lit up, sometimes you're blue. Just a phase, just a phase, just a phase. You're just a little different every time I look at you. Just a phase, just a phase, just a phase. It could be that you're loony. I know you're bipolar. Just a phase, just a phase, just a phase. But it's mainly about alignment and illumination solar. Just a phase, just a phase, just a phase. The way you change is unreal, and it got me kind of feeling like I somehow must be dealing with the cosmic chameleon. Just a phase, just a phase, just a phase the moon is going through. It's just a phase, just a phase, just a phase the moon is going through. You see, it all depends on where you're placed. Just a phase, just a phase, just a phase. When you're between the sun and earth, you don't show your face. It's just a phase, just a phase, just a phase. Past new, you reflect more and more sunlight. Just a phase, just a phase, just a phase. It's called waxing as you grow bigger from the ride. It's just a phase, just a phase, just a phase. At pressing your lip, it's just around the border. When you're halfway lit, it's called first and third quarter. It's just a phase, just a phase, just a phase the moon is going through. It's just a phase, just a phase, just a phase the moon is going through. And you come and give this face, your sunlit face becomes even greater until 2 weeks have passed since you were new. Full moon, you pull the night shift, stay up a little later. You rise at dusk, stay up the whole night through. Past fully get darker, but there's no sense complaining. Just a phase, just a phase, just a phase. Through gibbous quarter and crescent, it's clear that you're waning. Just a phase, just a phase, just a phase. How I love to watch your phases. It's almost hypnotic. Just a phase, just a phase, just a phase. 29 and a half days, your period sonata. Just a phase, just a phase, just a phase. Back to your spot ethereal, which some might find material. In 27 days, it's called your period sidereal. Just a phase, just a phase, just a phase the moon is going through. Just a phase, just a phase, just a phase the moon is going through. As a songwriter, I take a lot of pride in rhyming the word sidereal. That's a tough one. So, okay, so we've talked about the moon. But the moon is a beautiful thing to see any time of the year, especially those crescent phases through a telescope. Really good. But of course, there's other things to see in the winter night sky. Even the summer triangle you can still see in the winter sky. Now you have to catch it early. But the summer triangle is a triangle in the sky that's pretty easy to pick out. If you look in your western evening sky this time of the year, you'll be able to pick out 3 pretty bright stars. In fact, Vega is the brightest of the bunch. And Vega's down there in the lower right. It's in the constellation Lyra the Harp. And there's something very interesting about Vega. Vega used to be our North Star. A lot of folks think that the North Star is unchanging. But it's actually, it varies. Our current North Star is a star called Polaris. And it's only the North Star because the tilt of the Earth just happens to point. The geographic North Pole of the Earth points out into space, and its closest star that it's pointing toward is the star called Polaris. But the Earth, which is spinning, and it's on a tilt, kind of like a toy top, is slowly wobbling. And that precession, that's called precession, that means that it's not always going to be pointing at Polaris. It will point at other stars. And in fact, it was pointing at Vega at about 12,000 BC. Vega was the North Star because the geographic North Pole was pointing at Vega about 12,000 years ago. The process takes about 26,000 years to go through the full cycle. So it's going to be, again, be the pole star in about 14,000 AD. And the cool thing is that Vega is really, really bright. Polaris is kind of tough to see sometimes in relatively light skies. Vega is easy to spot. So navigating will get a whole lot easier in 12,000 years or so. So stick around. But this is the kind of an idea as to what that wobble is that I'm talking about. It takes about 26,000 years for the Earth to wobble one time. And therefore, Vega and any number of other stars are going to be North Stars eventually. In fact, our Polaris is not actually the best North Star that it possibly could be. By about 2100, it'll actually be closer to being the true North Star as the Earth continues to wobble just a little bit in the next 90 years or so. So there's Vega. Another interesting star in the triangle is Altair, which is down there in the lower left. It's in Aquila the Eagle. I should mention the distances to these stars. A lot of us, we get the misconception that the stars are on this dome of the sky and that they're all at the same distance. They're not. Vega, that we just talked about, is 25 light years away. That means the light we see tonight left Vega 25 years ago. Altair, 17 light years away. That means the light that left it, that we're seeing now, left 17 years ago. Cool thing about Altair is that it's one of the fastest spinning stars near the Earth. It spins once on its axis every 9 hours, compared to our sun, which on average spins in about 26 days, one time on its axis. And because of this rapid rotation, Altair is actually flattened out into what's called an oblate spheroid. Looks like a little M&M out there in space. Well, not so little. And finally, the third of the trio here is Deneb, which is the tail of Cygnus the Swan. In fact, you can kind of make out, if we can point out these stars here. Again, the triangle is made up of Deneb, Altair, and Vega. But you can almost see a little line of stars here. That makes up the body of Cygnus the Swan. Deneb is the tail. There's the head. And you can also see the wings then across. So that's Deneb. And Deneb is not even close to the Earth. It's 1,500 light years away, meaning, again, that the light that left it and is arriving today left 1,500 years ago. I should have mentioned. So it looks relatively the same brightness, doesn't it? And Vega's the brightest of the bunch, but it's still pretty bright. But it's so much farther away. This guy, 17 light years, 25 light years, 1,500 light years away. How the heck can it look so relatively bright when it's so far away? Size, brightness. It is a whopper. Deneb is a big star. It's a big and hot star. It's bluish white as opposed to our star, which is yellow. And it's 110 times as wide as our sun. I didn't mention, we mentioned comparisons between the moon and the Earth. The Earth and the sun. The sun is about 1 million miles wide, like we said, 8,000 miles as wide as our Earth. So you could put about 100 Earths side by side across the diameter of the sun, which means you can actually fit 1 million Earths in the sun. Same thing goes with the sun and Deneb. You could put 100 suns across Deneb. You could fit 1 million suns into Deneb. That's a whopping big star. That's why we can see it relatively easily. It's one of the brighter stars in the sky from such a distance. Okay, so we're saying goodbye to the summer triangle. Hello, winter hexagon. What's the easiest thing to pick out in the winter sky? What's the easiest constellation, I should say? A lot of folks kind of got messed up in the sky. You're so used to seeing the Big Dipper. The Big Dipper's a tough get in the winter sky. Much easier to find is Orion the Hunter, right? You probably can pick out Orion in this picture, can't you? See those belt stars? That's always the dead giveaway. That's Orion's belt. And we're going to start our trip around the hexagon by starting at Rigel's left ankle, or Orion's left ankle, which is a star called Rigel, the brightest star in the constellation Orion. And we'll talk a little bit about how to navigate. Once you can find Orion, which is pretty easy to do, notice that the belt stars will kind of line up. If you look up or to the right from the belt stars, they'll actually guide you to the second star in the winter hexagon, which is Aldebaran. Aldebaran is a red star, a red giant. It's, I think, about 42 times the size of our sun. And it is the eye of Taurus the bull. Continuing around, we'll get to Capella, which is in a constellation called Auriga, the charioteer. And Capella, to the naked eye, is just a single, it looks like a single star, when actually, if you had a strong enough telescope, you would see that it can be resolved into two separate stars. It's actually a binary star system. It's two stars in relatively close orbit of each other. So we continue on down here, we actually run into Castor and Pollux, which are the heads of Gemini, the twins constellation. So what we're seeing in the winter hexagon, we're actually seeing 8 of the 20 brightest stars in the night sky. And we're going through, I think there's 6 different constellations that you can see just by working your way around the winter hexagon. Pollux and Castor. Castor is a multiple star system. It's actually made up of 3 pairs of stars. I think I've got, there we go. So to the naked eye, it looks like one single star. With strong enough telescope viewing, you can resolve it into 6 individual stars. So it's a multiple star system. Continuing around the hexagon, we get down to Procyon. Procyon is the brightest star in the constellation Canis Minor, which is the little dog. Orion has 2 hunting dogs that hang out with him, the little dog and the big dog. Okay, so Procyon is the brightest star in Canis Minor, and then, not to be outdone, we have Sirius. And you can, again, easily spot Sirius if you can find the belt stars of Orion and work your way, instead of going up to Aldebaran, go down, and you'll find Sirius, the brightest star in the sky outside of our own sun. Very bright star. Why so bright? It's very close. It's only 8 light years away. The light that we're seeing from Sirius today left Sirius about 8 years ago. And Sirius has popped up in pop culture, hasn't it? Any Harry Potter fans? Right? Sirius Black. Right? And of course, Sirius is the name of a satellite radio company whose logo is the eye of a dog, the eye of the dog, the big dog. Like I said, it is the brightest star in the sky. It's easily spotted in the winter night sky. And it turns out one thing that a lot of folks do not appreciate is the fact that we don't see the same constellations year-round. Orion we see in the wintertime. We don't see it in the summertime. Why not? It's up during the day. It's still out there. You know, in the daytime, there are plenty of stars out there. We just don't see them because the floodlight of the sun is blowing out all those tiny little pinpricks of light. They can be easily picked out when there's no other competition. But once you get the sun involved, it washes out all those other tiny little pinpricks. So in the summertime, Orion is a daytime constellation. And the ancients realized Sirius must be a very either close star or hot star because it was so bright in their sky. And so you probably have heard the term dog days of summer. That came from the fact that Sirius, they would see Sirius rising with the sun. It was up during the daytime. And so they thought, well, gosh, it's so hot because not only is the sun up, but now we have Sirius adding its heat energy, and that's why it's so hot in the summertime. So that's where Sirius plays in kind of popular culture. Did you ever hear of the Pleiades? They're sometimes better known as the Seven Sisters. It's a star cluster. In fact, if you find Orion and find Aldebaran and go past Aldebaran, you actually will see a little smudge in the sky, even with the naked eye, called the Pleiades, sometimes called the Seven Sisters. This is a star cluster. These are stars that are about 100, they're, how far away? They're about 400 light years away. So the light that we're seeing is about 400 years old. They're very young, hot stars. They're only about 100 million years old. Our sun is 5 billion years old. So these stars are relatively, they're just babies. They've only been around for about 1/50th the amount of time that our sun has. Did you ever hear of Subaru? Subaru is the Japanese word for this star cluster, hence the logo. Okay, so as I mentioned, Orion's probably the easiest get in the winter night sky. Again, there's the belt stars, Betelgeuse, another one of the brightest stars in the sky. It's one of the largest stars as well. There's Rigel down in the lower left of Orion. And if you then look down below Orion's belt, you get Orion's sword, which is actually a nebula. It's a birthplace of stars. It's a big area of gas and dust where, again, stars are forming. In fact, this is the nearest star-forming region to our solar system. But again, you can use Orion to point you to, if you go up this way, you'll find Aldebaran, the head of Taurus the Bull. And if you go down this way, you'll find Sirius in Canis Major, the big dog constellation. Okay, finally, I did want to mention not necessarily a wonder of our current winter night sky, but a wonder centuries ago was the Star of Bethlehem. And there's been debate for, I guess, ever since it happened as far as what was the Star of Bethlehem. And to be honest with you, there is no real answer. Astronomers have tried to come up with ideas as far as what could have been happening in the night sky at the time of when the Magi were looking skyward. One possibility is this illustration, which was a conjunction of 3 planets, relatively rare, Mars, Jupiter, and Saturn. They got close to each other back in 6 BC. Now, one thing I should mention is that Christ was not born December 25th of the year 0. No one really knows. They know that they believe that he was born during the reign of King Herod. And Herod actually died somewhere between 4 BC and 1 BC. Christ was also not likely born in December. In Scripture, where they talk about the shepherds were tending their sheep, and tending their flocks, that most likely would have occurred in the springtime, when new sheep were being born. So it's tough to pin down what was happening, because it's tough to pin down when you're actually looking for things to have been happening. But some other options would be possibly a comet. Not likely. That's not a really likely possibility, because comets were pretty well known and understood. Comets were associated with portents of doom. You know, bad things were happening if a comet was in the sky. That would not be associated with this situation. Another issue is that there were no really good comets. Halley's Comet was around 11 BC. It may take us kind of out of the window of possibility. Also, a nova or a supernova. A nova means new star. It's actually not the birth of a star. It's actually the death of a star. It's quite often it's a star that's not bright enough to be seen in our sky by naked eye, but when it explodes, it produces a huge amount of energy, which then is visible. So that would be a possibility. If all of a sudden you saw a new star, that might be rather intriguing to magi who are astronomers. One problem is, with that theory, the Chinese have always done a good job of recording supernovas and novas, and there aren't a real convincing or big accounts of large supernovas going on around that time. There was a relatively weak one in 5 BC. Another possibility is another conjunction of planets, Venus and Jupiter. Relatively bright planets on their own getting close together would certainly be very, very bright. And that happened 2 times in the early BCs. Those planets got together in August of 3 BC, and then they also conjoined in June of 2 BC. Got relatively close together. And I think I used my planetarium program and kind of worked my way backward. And this is what it would have looked like in the Middle East in August. This would be August 12th, August 11th of the year. It's -2 in my number system, but it's actually 3 BC. So this is Jupiter and Venus are right on top of each other. A very, very close conjunction, which would have produced a lot of light and been rather eye-catching. So that would have been the first pass, the first conjunction, and then 1 year later, in June of 2 BC, they also got close together. This is in the western sky, again, a view from the Middle East. So those are all theories. No one really knows. I found this quote. This is a astronomer who used to run the planetarium in San Francisco. And he says, if you accept the story told in the Bible as literal truth, then the Christmas star could not have been a natural apparition. The reason being, in Scripture, it says that it stays over one place. And anybody who watches the sky knows that things don't stay in one place. The moon doesn't stay in one place. Stars don't stay in one place. the sky an hour from now is going to be different than it is currently because of the Earth's rotation. So to have a star hover in one place would not be a natural phenomenon, no matter what it is. Supernova, whatever natural phenomenon we try to explain it with, all those things would rotate. They wouldn't stay in one place. And so therefore, its movement in the sky and its ability to stand above and mark a single building would indicate it's not a normal phenomenon, but a supernatural sign, one given from on high, and one that science will never be able to explain. And that's it. I thank you for your kind attention. I apologize for the technical difficulties. Please do make sure to sign the sign-out sheet for my students on your way out. I think I hit all my points, despite my tap dancing here. If you'll please put the basketballs up front here, I'd appreciate that. Tennis balls. Put the bags of string back up. I should mention several of our instructors have iPads out in the lobby. If you want to see one of these viewing the sky programs at work, you can check one of those out.